Hi, this is Steve, U6WZ. Hey, how critical is that termination resistor at the end of your beverage antenna? How important is it to get that value just right? Hey, let's do some modeling and some field testing to study this. I think you'll find the results kind of interesting. I'm going to use 4NEC2 and we'll look at the effect of changing the termination resistor value on the far field pattern. I'm also going to talk about something called current taper and how even an unterminated beverage can still self-terminate and yield a directive pattern. Let's build a model for our beverage. Typical beverage wire can range anywhere from 1 to 1 3/4 wavelength long. It's usually a wire at either somewhere from 6 to 10 feet above the ground, is terminated to ground through what's called the termination resistor. And then at the feed point, somewhere from 5 to 600 ohm impedance is matched to the coax going to the rig with a matching transformer. There's different ways to model a beverage antenna. One is using something called min-neck ground. This is the min-neck ground solution. What it does is it implies a perfect ground underneath the beverage wire. And because of that, you can actually terminate a wire to the ground. In other words, a wire with a Z equal to 0 is terminated to the ground and connected to the ground. We model our wire 10 feet up, 918 feet long, 10-foot wire down, and we insert our load at this point. If we use something called the neck to real ground, we don't connect or can't connect the wire directly to ground. So we kind of fool the program. The model is the same, except at the termination end, we include basically a half-wave resonant dipole or 2 quarter-wave wires in a T configuration that the beverage will terminate against. The neck to real ground solution does not assume a perfect ground, but a real ground under the antenna. The importance of this, and the reason I'm showing you this, is we're going to talk about something called current taper. And that's important because real ground will account for what we're actually seeing in the real world. Here's those two models overlaid just so you can see them. In red is the mini-neck solution, and in blue is that real ground solution. More or less, the patterns are much the same. The notches are all in the same place. The biggest difference is the depth of the notches. Mini-neck shows a really deep notch, and that's not really correct. The reason for that is because, as I said, current taper isn't properly being accounted for, as it is with the neck 2 solution. I'm going to, from now on, be using the real ground solution, except a bit later when I talk about current taper. All right, let's see what happens when we change that termination resistor value in our model. But first, I just wanted to point out one of the nice things about 4NEC2 is it computes what's called RDF, the received directivity factor. I've highlighted it here on the splash page at the output of the program. RDF, for those that don't know, is the received directivity factor. It's a ratio between the maximum peak gain and the average gain computed in the full 3D hemisphere. It's a real handy metric to compare antennas for their receive capabilities. So I did quite a number of runs using different termination resistor values, and I've just summarized and selected 3 of those runs and overlaid them together on these 2 plots shown here. On the left is the zenith plot, and on the right is the azimuth plot. And the 3 runs I've run are 300 ohm termination, a 500 ohm, and a 1000 ohm termination. And you'll notice I've also plotted the RDF shown here for each of those runs. And first of all, it's pretty surprising, but really very little change in the actual RDF value of these antennas, with quite a serious change in value. I mean, this is a 40% or more change in value of the termination resistor. I've highlighted them here, and you can see that one of the things that stands out to me is that the pattern itself really doesn't change that much in terms of the null positions or the notches here. They all are essentially at the same zenith angle, and for that matter, the same azimuth angle. The only difference with the termination resistor value is the depth of these nulls. Okay, hey, check this out. I made, using the GIF animator in PowerPoint, I just strung together a bunch of plots. I did a series of runs using different termination resistor values, basically all the way from no termination all the way to a short. If you want to look at this a few more times, you could rewind the video, but it's kind of cool. You can really see how those notches don't actually change in terms of their zenith elevation angle. It's more just a matter of them getting deeper as the preferred termination resistance value is approached. A nice feature of 4NEC2 is it'll plot a frequency sweep against front to back and front to rear. This is that plot. On the bottom scale, you'll see it's run from 1 to 8 megahertz. We can select that. In red is the front to back, and in green is the front to rear. This particular run was done at the, let's say, preferred termination resistor value of 500 ohms. But what is this front to rear thing? I was able to drill down and get a little bit of information in the documentation, and it seems to me it's a ratio between the maximum forward gain and the average gain in the rear quarter hemisphere. You can actually specify in the program some limits. I chose 180 degrees in the rearward half hemisphere on the azimuth plot. And on the zenith plot, it's of course the top quarter. But it's a handy number, I think, because it more accurately reflects the overall directivity of the antenna rather than a specific front to back at a given wave angle. And you can see that on the plot because the green line, which is the front to rear, is fairly stable across frequency, whereas these notches appear to bump around. I did a series of front to rear sweeps here using those same 3 termination values that we did with on the other plots, all calculated on 160 meters. Definitely the best is the 500 ohm termination. Certainly 1,000 ohms is quite a bit worse. And obviously, shown on the zenith plot here, that's simply because we're getting better control of these rearward lobes. Even though, shown here as well, as the RDF, as we've seen before, really doesn't change that much, the overall received directivity factor. But that's why this front to rear calculation is pretty handy. It gives you a sense of the rearward rejection. So what's with these front to back peaks, though, speaking of which? They seem to really be very specific to certain frequencies. Let's have a look at that. If we look at this one at 1.7 megahertz, let's do a far field run and just have a look at that a bit more closely. That's shown here. In blue is the run at 1.7 megahertz. The front to back metric is a calculation always of the peak gain at the peak wave angle. In this case, it's at 30 degrees. And it compares that to the same 30-degree rearward gain at that angle. And of course, that's why at 1.7, you've got such a huge front to back value calculated here. But hang on a minute. In red is the 860 meter plot. And you'll notice that, obviously at the 30-degree wave angle where the line is, that would not compute as being a high front to back. But that's not because there isn't a deep notch. There is a notch, but it just happens to be up a few degrees in azimuth. I think trying to chase these, these high front to backs is a bit of a mug's game because how do you know in the real situation that you don't actually want the null, say at 40 degrees or 45 degrees? Do you really need it down around 30 or 25 degrees? Okay, let's talk about doing some field testing to evaluate our Beverage termination resistor value. In my opinion, you don't really need to do this. As I just showed, even a 40% change in the termination value has little effect on the RDF, but the rear null depths can be optimized, and this will maximize the front to rear, which is beneficial. Let's go through some field measurements that I made. It's pretty interesting. I think you'll see that the field measured changes are pretty subtle, but it does show some interesting characteristics of the Beverage antenna. Okay, first of all, what do we need to do, or what do we want to do here? Well, let's use the analyzer and sweep the raw Beverage wire at the feed point, and then change the termination resistor. This is a Google Earth view of my QTH showing the various wires throughout my area. So, for example, my south wire shown here is about 950 feet long. So the plan would be, let's hook up the analyzer at the feed point and then walk to the termination and let's say, we'll short it out. Then we'll walk back and do a sweep and then save the file. And then we'll walk back and then say open the termination. And then we'll walk back and save the file, or rather do a sweep and save the file. And, then we'll walk back and change the resistor to say 500 ohms and then walk back and do the sweep and save the file. And well, anyway, you get the idea here. That's a whole lot of walking, and I had no intention of doing that. So at my station's a remote station and fully internet connected, and so my plan was, and what I did do was I installed the analyzer in the shack, which is shown here where my cursor is. And then I did what's called an open short load calibration through the feed line, shown in yellow, to the feed point. Very easy to do and really quite accurate. In fact, I did a comparison between that sweep and one with the analyzer right at the antenna, and that they're virtually identical. So now with that in hand, I'm then able to be at the termination, and then using my iPhone connected through TeamViewer or any other remote desktop application using my LTE data connection. I'll then just do a sweep and save it on the PC in the shack, change the resistor value, open it, short it, do whatever I want, save the file, and save it for future reference. And really easy to do, and certainly saved a whole lot of time. Here's the feed box showing the coax connection. I just built a simple little jig here using a PC board F connector. This is where I would have done the open short load calibration. The one wire at the top here is connected directly to the beverage wire, the other to ground. And this is the termination. I had pulled a linear potentiometer out of the junk box. It's a 250 ohm pot, and added a couple series resistors, so I got a range of somewhere between 340 and 580 ohms. So I was able to do a number of resistance sweeps as well as a short and an open test. Okay, so before I show you the results of that, though, it's important to at least have a feeling for what the beverage theory is, because that's what we're really testing for. That is, the beverage is acting kind of like a transmission line, with the beverage wire itself, some height above ground, acting together in concert with the ground being the other side of the transmission line. In other words, like a piece of twin lead with the wire and the ground representing the two conductors, and it's terminated, and it's the resistor. We want to match what we call the characteristic impedance of this transmission line, or surge impedance. We can actually calculate that. There's a formula. It's 138 times the log of 4 times the height of the wire above ground divided by the diameter of the wire. My 14 gauge wire is 0.07 inches, and 120 inches for 10 feet would suggest that this preferred impedance ought to be in and around 500 ohms. Let's go back to that mini neck ground solution model that I talked about at the beginning of the presentation here. That's the one where we're using a perfect ground under the antenna, which has no losses. We're going to do 2 runs with this. One where we terminate the beverage, terminate the wire in its characteristic 500 ohm impedance, and another one where it's open. Well, in the model we insert 1 million ohms. One thing that 4NEC2 will do, which is kind of handy, is it'll plot a current distribution along the wire. In the diagram here, the purple is the wire, the model, terminated at the blue square here. The green line is the actual current, and its magnitude is based on its height above the x-axis. The model on the top is where it is terminated in its characteristic impedance, and you can see it's a nice flat line. The plot below is where we've done the sweep with the termination open. And you'll see we end up with these standing waves of current on the line. Well, that's because it's not terminated properly. So the signal is hitting the end and is reflecting back along the line, instead setting up these standing waves. The curious thing is this is a 918-foot long wire, or around 1 3/4 wavelengths. Well, if we count it out, that's 1 wavelength, and that's 1.5, 1.6, perhaps the electrical length of the wire. So if we do an SWR sweep in the same model, you'll see that if it's terminated at 500 ohms, it's a nice flat SWR. But if we misterminate it, well, in this case 300 ohms, it's kind of bumpy. You overlay the two, it looks like this. Well, okay, here's the actual field sweep, and you'll notice this kind of doesn't look the same. It's kind of, the 2 sweeps, one no termination shown in the light line, and the heavy red line is the terminated at 500 ohms. They're kind of converging here in the higher frequencies. I'm going to talk about that in a minute. You'll see a number of these plots. So this is a sweep in the field from the AIM analyzer. The bottom axis goes from 0 to 8 megahertz. Well, the sweep actually goes from 1 megahertz to 8 megahertz. And SWR is plotted on the axis here, shown in red. In this case, it goes from 1 to 1 to 10 to 1 on a log scale. There's a reason I've done that. So the other thing we can do is, and this is important to understand what's going on here, let's look at the real ground model that we built. where we're using this half-wave dipole termination and have real ground underneath the wire. We'll do a similar series of runs. In this case, there's no termination, and you can see that we have this, spiky SWR, but it tends to be flattening out further along. And if it's terminated in its characteristic impedance, it's a lot flatter. So we overlay those two, and it kind of looks like this. Well, this is looking a lot more similar to what we're actually seeing in the field. So I'm going to talk about what's going on there in a minute. But let's change the resistor values here and see what happens. So here's where in the field, I did a whole lot of sweeps. I did a whole lot of different sweeps. I did open, I did shorted, I did a whole bunch of different resistor values. But I've just selected these because these are, kind of show the meaningful end members of where we'd actually try and change things. Let's do a zoom in and look at it here. These are pretty subtle SWR changes. So here's the zoom in. The heavy line is the 450 ohm termination. You can see it's bouncing around a bit. In the light red line is the 580 ohm termination. And in the line with dots, it's the 340 ohm termination. So okay, it's pretty subtle, but I think this would suggest, based on our modeling, we want this SWR profile to be as flat as possible. And I'd say, 450 ohms looks like to be the preferred termination. But, it's pretty subtle. So what's going on with this convergence down here? Well, it's definitely happening when it's no term and resistor value. But when the beverage is actually terminated, it's even more dramatic, whereby there is no change here. These things are all converging and being the same. Well, this is because the wire is beginning to self-terminate. In fact, if we did a run, did a far field pattern with no termination at all, this is open on 40 meters, you'll see that we're actually developing a directive pattern, even though there is no termination at all. And that's because the beverage is actually self-terminating due to the current taper going along the wire. And that's because of the lossy ground. And in fact, if we do this same far field pattern on the mini-neck ground, where you've got a perfect ground under it, well, it shows that there is no limited directivity. It's truly a bidirectional antenna. And that's because, of course, we're not properly accounting for the ground losses under the antenna. So a little bit more about current taper. This is the difference between the current taper at 160 meters on the top line and on 40 meters. You can see that the wire is really tapering out because it's so many more wavelengths long as it goes further down the 918-foot wire. And in fact, this is reflected in the far field pattern. This is the 918-foot wire, the same wire with no termination. Well, and it is still acting pretty much like a bidirectional pattern. And that's because this wire, as a measure of wavelength, is still not that long. By the way, this still shows a decent RDF of about 10.5, which isn't bad. I mean, that's comparable to some terminated loops. And that's mainly because of the side lobe rejection here. But having said that, it'd be a pretty crappy antenna if you're really gunning for a decent front to back or rearward rejection. Current taper over poor versus really good ground on 40 meters. You can see it makes sense that there's greater current taper as the ground gets worse. What about the effect of wire? Well, the wire itself ends up with some distributed resistance along its length, which actually also contributes toward the self-termination as well as the poor ground. So I did 2 runs. I was able to select stainless steel wire, which is greater resistance than a perfect wire, and you can see, of course, that the current taper is less dramatic with using a perfect wire. One other thing that's interesting here is if we do 2 runs, one with a mini neck of 500 ohm termination on 40 meters, this is terminated. You notice the current taper there's nothing using mini neck, and that's what we were just explaining. And this is with the real ground solution. And you can see that, of course, there's the current taper shown on the diagram to the left. But I'm going to flick back and forth. Look at the zenith plot here. So this is mini neck, real ground, mini neck, real ground. So you can see that using real ground, we're filling in these notches, which is more correct than the mini neck solution. Okay, that's cool stuff. A few comments regarding comparing antennas based on the RDF modeled metrics. 4NEC2 uses the peak gain wave angle to compute RDF. Now, other programs may use a specified wave angle, like 20 degrees. So if you see that some other quoted RDF numbers for beverages differ from mine, that could be the reason. Another reason is that, the beverage's RDF will depend on the type of ground used in the model. For example, I did a few runs on my 918-foot wire, and from good, average, moderate to poor, it can range anywhere from 12.9 dBs to 11.7, depending on the ground type. All right, in summary, look at the overall RDF performance of a single wire beverage is not greatly affected by the termination resistor. I showed even a 40% plus or minus change in that resistor has very minimal change on the RDF. However, the front to rear and the rear null depths or the notches, that does change quite a bit with the varying termination resistance. But really a precise termination value, plus or minus even 50 ohms really isn't necessary. If you build a beverage, terminate it with a 400 to 500 ohm resistor and it'll perform just great. That's assuming you got a 7 or 10 foot high wire. Field testing can be done to help find that optimum termination by just observing the SWR profile. But as I showed, that measurement can be pretty subtle. And because of current taper from the lossy ground and the wire resistances, beverages will begin to self-terminate when they're long enough. And even an unterminated beverage has pretty good RDF because of the side rejection. But if you want a bidirectional, beverage, make sure that it's not more than 2 wavelengths long. I hope you enjoyed the video. Go build a beverage if you have the room. They really are easy to make. A wire strung above the ground, a couple of copper pipes hammered into the ground, a resistor, and an easy to build matching transformer. Also check out my other videos, especially the ones about beverage field construction tips and the one about building matching and termination boxes. 73, Steve, V6WZ.